Here's problem 8.26. The two masses in the figure are released from rest. After the 3 kilogram mass has fallen 1.5 meters, it is moving with a speed of 3.8 meters per second. How much work is done during this time interval by the frictional force on the 2 kilogram mass? So we have these two masses. We have a 2 kilogram mass here and a 3 kilogram mass here. And the 3 kilogram mass is going to fall a distance of 1.5 meters. So at some later time it's going to be over here after it has fallen 1.5 meters. But it is connected to the 2 kilogram mass, so that mass is also going to move forward that same distance of 1.5 meters. Also, we're told that the mass after it has fallen is moving with a velocity equal to 3.8 meters per second. Let's call this point B, this secondary point. So that'll be our velocity at B. And for that matter, the 2 kilogram mass is also going to be moving to a new point B and moving with the same velocity because it is connected to the other mass. So everything is connected together with a taut string. Our initial velocity at point A for both of these is 0 because we start from rest. So this is point A here, and this is point A. Alright, so we have that information. We want to find the work done by friction along this way. Now there is a frictional force possibly against the motion like this, but we just want to find the full quantity of that work done, and so we can do that using the one equation to rule them all. So we have the kinetic energy at A plus potential energy at A plus any work done along the way equals kinetic energy at B plus the potential energy at B. Now we can define our potential energy at B to be 0, so the lower height as being our 0 height, and the height for the 2 kilogram mass doesn't change, so we definitely define our UB being 0. We started from rest for both masses, so our kinetic energy at A is 0. So we strictly have that the work on the system is equal to our kinetic energy at B minus our potential energy at A, which is the potential energy of the 3 kilogram mass above our 0 height. Our kinetic energy at B is 1/2 both masses moving with the same speed, so it's mass 1 plus mass 2 moving with a velocity of B squared minus our potential energy at A, which is mass 2 G times our height. So we have 1/2 2 kilograms plus 3 kilograms times velocity of B squared, 3.8 meters per second squared, minus 3 kilograms times 9.8, and we were 1.5 meters up at that point. This is equal to a negative 8 joules. So the work done by friction on the 2 kilogram mass, because that's where the friction is acting, is negative 8 joules. And we didn't have to figure out the frictional force. If we wanted to, we could say that this work is equal to negative frictional force times distance. So that frictional force would be equal to negative work divided by distance, which would be a negative 8 over 1.5 meters, and that is equal to 5.3 newtons. That would be the frictional force that is acting on the 2 kilogram mass, but we weren't asked for that. We were asked for the work done, and that is a negative 8 joules.